morning, everyone. Today we're going to think about relationships and the entities that they connect together, and how to model them into a graph database for Spring Boot applications that are using Neo4j. So we all live in this world where data is highly interconnected. But imagine that the data that you're working with simply does not live in the tables that you use to plot your data in. And the reason why they don't plot that easily into those data tables actually matters to the business. You're working with data that you try to store into tables, and somehow you need to relate it to one another, and you always end up with this coupling table where crucial information about your domain is stored, and it's quite hard to get it out there with simple queries. When we as developers are thinking about storing data, or at least I am thinking about it, I immediately think of relational databases by the means of Postgres, MySQL, or Oracle. Those are my go-to options if I want to store data without even thinking. But sometimes those solutions are either too strict or too expensive, or there are many reasons why you don't really want to go to it. Then you can also think of NoSQL databases. Think of MongoDB as a document store, or Redis as a key value store, Cassandra for white column storage. But if you think of graph databases, my first hit when I'm looking for options would be Neo4j. Just be aware that this is not a project pitch for Neo4j. I'm not working for Neo4j. It's the only graph database that I used to work with. So that's why I'm talking about Neo4j today. Who am I? I'm Paulien van Alst. I'm a Java developer, Kotlin developer at OpenValue. I'm a consultant and working for companies that are facing innovation challenges. I'm also a co-organizer of the Java user group North in the Netherlands, it's up north of the Netherlands, and I live there together with my boyfriend, 2 kids, a dog. We try to rebuild our home and maintain a huge garden. Somehow I have some time left to come here and speak. So let's forget about relational databases and plot our minds to graph databases. Graph databases can be described with first-class citizens that are nodes, relationships, and properties. In some articles, you might find the terms vertices for nodes and edges for relationship. Most of the times, those are more than mathematical articles. I won't be using those terms because I've already been told with nodes and relationships. So that's why I'm talking about nodes and relationships in this talk. Properties are also first-class citizens in graph databases as they add valuable metadata to your graph. A graph can be, for example, something like this, where you have several nodes, each color describing the kind of node that you can see here. In blue, an author. In purple, recipes, and in orange, a keyword that can relate to those recipes. And as you can see here, not only the nodes have types, but also the relationship do have types. For instance, the relationship between an author and a recipe is typed by the word wrote, and pesto relating to a tomato mozzarella recipe by the type keyword, which already indicates that relationships are storing valuable information regarding your domain, valuable functional information about your domain. Query language that you will use on graph databases highly rely on pattern matching, which in my regard is very valuable because it's a very visual query language. This is just one example that could show a graph like you're shown here. You can see here that it's highly descriptive and matching the graph that you are seeing. Some common use cases to use graph databases, obviously, it's very valuable for domains where data is highly connected. Entities should not stand on their own on a graph. Mathematically, a dangling node could represent a graph. But is that a useful graph? Just one node with no relationships? Well, no, it's not. And there's not only thing, relationships are very our own part of the domain as well. They hold very valuable information of that domain. Some concrete examples of those data sets are obviously a family tree. If you're thinking of a graph in your mind, your first go-to option would be a family tree, where family members are linked to each other with different kinds of relationships. But also social networks. Think of a school structure describing students and classes, courses that can be followed whatsoever. Or HR administration relating employees to their managers or departments and positions. Another very common example could be investigations of Panama Papers, where actually data analysts or researchers could identify communities in those Panama Papers by investigating the data that is in there through a graph database. The strength of a graph database is, again, the relationships directly in the model. I've stated that already a few times. You don't need to write down very complex join query to find out all the data that is related to one another. Although you can, so if you love those queries, you can still write them, no worries. You are not obliged to a tight schema to model your data into, but no worries. It doesn't mean that you can do anything on the graph that you are working on. You can still set some rules and set some structure in. No schema doesn't mean entire freedom, because you can still you can still tune your queries by using indexes or imposing constraints on the data that get inserted in the database. So you can still make sure that the graphs that are inserted in a certain instance is compliant to some of those rules. And which is also pretty valuable is that you can have advanced analytic tooling into a graph database right ahead. You don't need to figure it out all by yourself. Now, as I said, today we're going to talk about one particular graph database, which is represented by Neo4j. So what about Neo4j? Neo4j is a pretty mature database, I would say. It guarantees ACID transactions, it connects with the BOLT protocol, which is carried over TCP or WebSockets, and it ensures that your queries are properly executed from your application to your database. It uses Cypher as a query language, and it has Neo4j desktop as a viewer on your database, which can be viewed as DB, which is your database viewer, sorry. Cypher is its query language and is pretty declarative. It's close to the natural language, designed to graphically match the graph, and it's highly relying on pattern matching. Those 3 bullet points, I put them there separately because I find them very valuable, and in my experience, it helps out to write out your queries and actually discuss them with your business owner, business analyst, or anyone that has functional knowledge of your domain. Because the language is so graphical and a bit less relying on highly Boolean logic, it's easier to just level with people with functional domain knowledge. It's also come along with a library, the APOC library, which stands for Awesome Procedure on Cypher, which holds a lot of procedures and functions that can help you out with many types of things, like collection manipulations or graph algorithms, or here they're stating also data conversion, but there are a lot of functions already in there. They're not there by default. As you can see, this is a screenshot from a Neo4j desktop application where you can install local instances. You need to install it by yourself, either if it's locally on your laptop or if you're deploying into a cloud environment or in your Docker image. But it is there, also in the community editions. So let's discover a graph, because today we're going to do some data modeling. And before doing some data modeling, I want you to see how it is to query a graph and to get into your head how you would look at such a graph. So that means that I'm now going to this Neo4j desktop, which is a product that you can just download and install on your local machine. And in that local machine, you can install, it's selecting everything, just some instances to play around with. You can even install some graphs if you want just to play around and to discover how it is to work on a graph. I would actually recommend to do that before you start working on a project with Neo4j. There are a lot of graphs out there that you can rightly insert locally, either on the Neo4j website, on Kaggle, or other data platforms. A nice feature, I think, of Neo4j as well is that in an instance you can actually maintain several databases, which can be nice if you want to discover several domains or play around with several graphs into your applications. You only need to deploy one instance. As you can see as well over here, you can connect to it using that particular Bolt protocol, which always will expose this type of port. And if you want now to discover what's in there, you can just connect to that graph and start querying. Now, if I want to start querying on my graph, I can do so by starting with the keyword match. Match is a keyword that you will always use to try to find something into your database. Now, I want to start querying just one single node, which is of a type utensil in this example that I thought of. To declare a type, I need to use a pre-leading semicolon to make sure to indicate to the query this is the type I want to look for. And then I want to return that particular node. I will do so by assigning a variable to that node, which is in this case just the letter U. This query will actually return all the nodes that are matching this type. In this particular graph, there are only 3 of them. If I only want to return one, I can just limit it with the keyword one. So those queries are not that different from SQL, but a bit more descriptive using those curly brackets. If I now want to go and find out a more particular entity, for instance, one that is matching this name, I can actually start to use those properties that are declared on a node by just opening curly brackets and then using a dictionary to describe the node with a certain property I'm looking for. And that will exactly find the same node over again. You can do the same if you don't really like this syntax. You can approach it a bit more with a SQL-like instance where you can say, I want the name of my node to be equal to this certain field I just copied. So then you're finding back the semantics of a SQL database. Both are valid and both are doing the same thing. The query planner will exactly execute the same thing. But we are here not to find single entities. As I said, it's not very useful. We're also here to find relationships. So now let's see if I can query a node that is related to, let's say, a recipe. I want to see this whole relationship, this whole path, so I will actually assign values to both the node, the relationship, and the target node. And make sure that this is returned. Well, I need to put some commas over here, otherwise it won't return it. And then I will actually retrieve it right away. I would like it to show it a bit better. Here you can see the whole path that I was querying for. I'm talking about paths. Actually, you can also describe it as a path by assigning to a value, p, and then return it in the same manner. Now, this is just one path, one node relating to one other node. I can also say that I want, for instance, because I know this is the case in this graph, that I want to find an author that is related to ingredients using a path with any type of length. Then you're using the asterisk, and that will return all the paths that are relating an author to an ingredient, no matter how many hops it needs to take in the graph. And this will actually return the whole graph that I stored in this database, because I said the authors are my top nodes in this graph, and my ingredients are my leaf nodes, and it's returning all the paths between those top and leaf nodes. So those are some very basic understandings of querying. I forgot just one, is that I can also, if I want to specify a type of relationship, I can actually specify it again by using a semicolon into my relationship just to return that path. This will actually return all the authors related to some kind of recipes. Actually, you will see that this is not, yeah. This relationship also has properties. So this again, you can actually look out for properties like I did for nodes. You can also do that for relationships. This should work as well. These are all the relationships, all the recipes that have been published on a website, for instance. So very small introduction into Cypher. There are much more features that you can look into, but that will mean that I will go way over time if I introduce that to you all. Just get it into the back of your head, because now we're going to start to do some data modeling. Because Neo4j will now be used, actually, to express our domain. We're going to do some data modeling. And why I wanted to give this talk is because on several assignments that I worked on, I discovered that the investment of time prior to implementing a solution with Neo4j was very too short at the end, or the time they invest to model the data was too short, and they ended up with a solution that they actually didn't really like, and they blamed the tool. It was actually making or breaking their experience. Well, it's really important to invest some amount of time, some significant amount of time, before starting your experience. And by experience, I mean going to production. When you're going to start your data modeling, it's important to involve everyone, both your business owners, testers, developers, architects, and whoever has any knowledge or something to say about your domain should be involved in the discussion about how you guys are going to model your data into a graph solution. Just because there are plenty of graph solutions that will fit your domain, but there will be only a few that will actually fit your challenges. If you start to model your data, you will start by just drawing your main entities. If you're going to model a recipe inventory, 2 entities will come straight into your head at first. Recipes and ingredients, that's the most obvious part. What's good to do then is to start how they could connect to each other. They can connect from recipe to ingredient, but obviously they can also connect starting an ingredient to a recipe. And what is important to do next when you're trying to model the data that you're working with is to write down the questions you want to ask to the domain. Because in this particular example, if you're looking for the ingredients that are needed in a recipe, if that's one question that your application will ask for, then it's obvious that you will want to model the relationship starting from the recipe going to the ingredient, because the entry point of the querying answering this question will be the recipe, and then you're going downwards the graph. But if your application will be more focused on finding ingredients, finding recipes that are related to recipes, then you will actually want to model the relationships all the way around. This actually really matters on the reading performance and also on your understanding of the domain you're working with. If you don't do this correctly, you might end up with queries that are really poorly performing. And then you will think that Neo4j is not really good at reading, which actually is. Test those questions then again against the entities and relationships that you have drawn in step 1 and 2. And that is actually your plan of attack when you start modeling. You start to draw your main entities, you start how to draw how to connect to each other. You write down your questions you want to ask to your domain, and you test those questions to see if you can answer them. You evaluate how that went, and if that went easy, because if it's hard to write out the graph that will represent the response, it's probably hard to write down the query as well. And then you start over again until you have no awkward solutions anymore. Yeah, because you will have, while doing this exercise on a more industry challenge, you will see that this will take quite some iterations. At one of my clients, we spent actually 2 days remodel a graph, remodel a solution. One of the challenges that we had was to forget about the graph that we already had running in production. That took us half a day. And then we finally ended up, together with a consultant of Neo4j actually, with a graph that was very much more performant. By investing those 2 days, we managed to get rid of a caching mechanism implemented in Redis, and we could directly just query our application to Neo4j without using any other caching than the caching of the database. So modeling a good graph is very, very important. And it's really valuable of your time. But don't take months either. Don't overdo it either. But it's important just to do this exercise. And again, I don't know if it's very visible on this slide, but the drawing part here is very important. Forget about the queries, forget about coding, just start drawing, because the power of graphs is actually that this visualization part is so strong. So, as you might notice, today we're thinking of recipes and ingredients, and this was just one very, and we are going to model it ourselves. Let's start off with this first solution that we drew until now, where we have recipes and ingredients connected to each other. And let's think of a very, very simple recipe inventory of a sandwich place. Then on my whiteboard, I will start drawing 3 ingredients. Why 3? Because most of the time, I will have more than 2 ingredients into a recipe. So I just draw 1 more on my whiteboard. I also draw my recipe note. This is the most intuitive solution of a graph that I could think of. The most intuitive relationship is just, I can just call this relationship that an ingredient is used in a recipe. Make sure that when you're drawing those relationships, you don't use very generic types for your relationship. Relates to, is part of, is child of. Because those are very too generic and fitting to each and every domain that I can think of. But what you want to do is to find terms that are really suiting your domain and expressing a sentence. This is fine, used in this way too generic, but this is the starting point of my data modeling. If I then want to describe how a tuna sandwich would look like, very simple tuna sandwich, so to say, this could be it. I want to put some salad, I want to use some salad in it, some tuna spread, and some bread. This could be fine for a very small sandwich store that you will find here in the city. But as that sandwich store is expanding and becoming a way more international sandwich store that I can find back in Amsterdam in the Netherlands, the amount of recipe is growing along. And then we can end up in one bottleneck of this graph, is that we might end up with this kind of solution with 2 highly connected nodes. Because a lot of the sandwiches we eat nowadays, this went too fast, is that they have some salad and I have some bread. So if I'm going to a graph that is representing 1 million of recipes, all holding bread and salad, those nodes are being highly connected to each and every recipe. And they become a bottleneck into querying. But this graph would still hold for a very small business. So it's a good graph in a way that it's simple to insert, it's descriptive, it's easy for simple questions. And the con is that it's a monotone graph when your data is growing, and then your solution is not fitting your business anymore. So another thing that you could say, instead of having simple ingredients, you could say, I have vegetables, I have spreads, and I have all kinds of breads. I've now become a more elaborate sandwich company. And I still have recipes, because recipes was fine. And now you can think of that maybe I want to insert other kind of relationship into my graph. I want to say how vegetables can be put on a spread, for instance, or how the spread is put on the bread. I can still find out another name for the relationship to the recipe. It's good to change those obvious names towards your iterations of designing a graph. And now I've got much more information into my graph, because actually the bottom row is describing the recipe and the steps I should follow just to create that sandwich. So this graph is already telling me more about the domain than my previous solution. But imagine I want to request something about ingredients. That was not possible when I was calling them vegetables, spread, and bread. But fortunately, in Neo4j, you can actually add a secondary label to your nodes, which can then gather all those nodes back again into one type. Then you can choose when you're querying whether you want to target only the vegetable nodes or the ingredient nodes. For your query planner, that can matter, and that can actually help you out with some of your queries. So if I'm now going back to my tuna sandwich example, you will see that the whole recipe is written down. So then again, this is another graph that could be fitting my solution of a sandwich store. The pros of this example is that the recipe can be read from the graph. Ingredients have all their own type. The cons is that it can be too specific or too complicated to proceed with the business application. And maybe it's also very hard to define when something is a subgroup or not. For bread, maybe it was very obvious, but for the spreads, maybe not, or there are other challenges. So be aware that if you're making nodes more specific, that you can maybe make them too specific. So there is a balance to take there. And make sure that you don't have many relationships between ingredients, for instance. We're saying salad is topping off the spread, but then you need to add some information in which recipe that's the case, and so on. And then it becomes a bit more too complicated. So that's a balance that you can take. These were two examples on how you can model this challenge. What you want to look out for during your data modeling is to look out for extremely highly connected nodes. It's very easy to start small. You should start small. But as your graph is expanding, highly connected nodes or dense nodes or whatever you might call them can form a bottleneck into querying for the data planner, for the query planner. You must imagine that sometimes the query planner needs to discover the whole graph to find out some paths. Even if there's one highly connected node, it will always go through that node, which is highly expensive. The direction of the relationship matters. The query planner will always go from top to bottom. So it's also important to keep into your mind. Define your indexes wisely. I won't elaborate on that because that's a separate talk. But keep in mind that graph databases do use them. And it's a mature database, so that means that you can always use an explain plan and a profile before running your query on your production data set, which you should actually do. Some tips to solve all your challenges when you're doing your data modeling. Try to make them as specific as they're fitting the data, your domain, your functional domain. Change the node type until you have this less awkward name. The same holds for relationship. If very connected nodes are popping up into your domain, you can also try to categorize them using properties. That can also be a solution, as properties are also first-class citizens in your graph. And always challenge the business requirement. Is it really necessary right away? Can we postpone this kind of query? Can we maybe discover a bit more about this domain? And always ask which are the most frequent queries, which one will be involving a lot of data and which one are not. Another thing that you should be aware of in a graph is the path transversal. If you model a graph that looks functionally correct, for instance, this one is to is a graph modeling how you can build up a pizza. But then your business will always want to require always want to ask which kind of cheese will be on the pizza, which is a leaf node in this example. Then the database always needs to go through that leaf node to check if the path is compliant to the condition you are meeting up. That's very expensive as well. One way to solve this is to maybe put one direct relationship between your top node and your leaf node. But that's something you should think of if that's a valuable one. But leaf nodes are really expensive to query. So that's important to keep in the back of your mind. Now, this was a bit about the data modeling. And now let's see how this can be put in practice into application. The application that we are going to see, you already saw a bit when we were querying with Cypher. It's a data set, recipes that are written by authors. Each recipe needs ingredients and are composed of steps. And of course, they require the use of utensils. The question that you could ask to such a graph is that you want to look up recipes and ingredients. You want to list the most used ingredients, list all the recipes and group them by authors, for instance, and which authors are making the most diverse recipes using the most ingredients per recipe. The graph of a domain that, of the application that I'm going to show you is that an author can thereby write a recipe. A recipe requires ingredients, but sometimes you also have optional ingredients. So this shows us again that you can even write down two different kinds of relationship between two entities. A recipe is prepared by steps, and utensils are used in recipes. Our tech stack, it's a Spring Boot application written down in Kotlin using Spring data to do the connection with your Neo4j graph. And I deployed my Neo4j graph locally on my laptop, but you can deploy it anywhere you want. So let's show you some code now. And I hope this can be seen from the back, because otherwise I will increase the font a bit. Neo4j will easily integrate with your Spring Boot application as you have a Spring Boot starter, which means you can use auto-configuration just to configure the connection with your database, stating the Neo4j, your authentication, and my highly secret password. And then even if a good thing to remember when you're working with is that you can always set the logging to debug if you want to monitor the queries that are being generated. If I now want to put my graph model into my Spring Boot application, I can describe it by using entities. As I said, there is no schema imposed in Neo4j, but the application that I'm now going to describe actually has a schema. However, if my application is not going to find any nodes compliant to the schema described here, it will just return nothing, so nothing will break. If I want to describe a node in my Spring Boot application, I can just write down a class or a record in Java, annotate it with node. Of course, my entities are still database entities, so they should have an ID with a generated value. And that node, in this case, is related to recipes. However, what you would see here is that I don't have a list of recipes, but I have a list of relationships. Those relationships are targeted with an annotation, which declares the type of my relationship and the direction. It can be outgoing or incoming. And the list that I have here is of the type of the relationship. The name has written, and it describes all the relationship properties, so also the properties that I can put into my relationship. And this is the place where I will see the target node of that relationship. That is listed here. And then the recipe actually is modeled in the same regard. This one is a bit more complicated. It has different kind of relationships and some kind of properties. Important to note is that you can also insert durations in properties. Duration is just a type in Neo4j, which actually also maps pretty fluently between Java and the Neo4j type. Now, if I want to query that data in my application, I can just declare Spring Data repositories. There are Neo4j repositories already there. You declare them as you would declare a JDBC repository. This one is actually mapping authors which have an ID of type long. I can declare generated queries by just write them out with the Spring Data mechanism. So this one is finding a name containing a part of a name. So I can do some text search in Neo4j as well. But I can also write out my own queries. So this one is just a Cypher query that I could also have written into my Neo4j desktop. If I don't want to retrieve any entities or nodes or relationship, but I just want to find something else, like I had to find it, but some kind of statistics, I can make use of projections. Projections are just another representation of the data that you are retrieving. In this query, I'm actually retrieving all the ingredients and how many times they are occurring into a recipe using the count function. I'm using this projection, most used ingredient row, that only holds 2 fields. And then the mapper will automatically fill in my bean. If I'm now going to my API, I can see how those queries are evaluated. Let me see. I need to start it over. Let's see. Oh, here it is connecting right away with my Neo4j database. Here you can see it. It has connected to it, and it's logging a lot about all the nodes that it has detected. If I'm going to my browser where I've actually stored my Swagger UI, here I have some recipes. I'll just make it a bit bigger. And I can actually start to request recipes that are, for instance, containing the letters MAD in this particular order. And it's case sensitive. And hereby I can retrieve a recipe which is actually called Madeleines and not MAD. You will see that now the Spring Data has generated a query that I have not written down. It's here a recipe that contains, that has a name that contains the value that I have given or the description that contains something that I have given. And that was actually the query that was generated with this one. This one I have written out, but for ingredients is actually the one that Spring Data has generated. So let's see. Here I have it. Here I have flour. I have several types of flour into my domain. And if I go back to my logging, you will see that now it has generated. Here it is. This is the query that Spring Data has generated for me. And this is the function that was corresponding to it. You can also use the Spring Data methods that you will usually find. Like if I want to find all the recipes, I can just say here, this is my endpoint actually. This will find all the recipes. I did some mapping not to show all the properties of the node. And if I go then into my logging, you will see that here it was matching all the recipes and returning them. And if I go to my endpoint and look out for my get all recipes and go to my service, that is actually calling the find all solution that Spring Data will propose to lots of those Spring Data repositories. So that's also neatly integrating with Neo4j. I will go back to my presentation now. So that was a bit of the coding. My lessons learned, again, from the project I've worked on, is do not try to model too many of the possible future requirements ahead. Try to stick to the requirements you are facing now. Embrace the flexibility of the graph database has to offer, because you're not strictly tied or married to the graph database you're working on. Use the constraints and indexes that you can declare on, and think of your architecture. What about the future, actually? But because you still want to get this in the back of your head. Well, you don't know about it, but you can still make sure that you have a good ETL process in place to be able to remodel at any time your graph. And there you will find back the relational database, where you don't store your relations already, but just store your data as flat as possible. There's some awesome process that will actually then insert it into your graph database to enable you to have some flexibility to change solutions, because it's really, really, really challenging sometimes. But it's really nice to work with. So I hope this short introduction has inspired you to maybe play around a bit and help you out with your challenges. Thank you for attending this talk. And I'm curious to see if there are any questions asked.
How do you manage version freeze?
Yeah. You mean if you want to version your graph?
You already rolled out some production database.
Yeah.
And you remodel some.
Yeah. You can insert as many graphs as you want. And what you can do, but this is a very hard challenge ahead. We asked it to the Neo4j consultant that we had over, and they didn't find a solution yet to implement it right away. You can start introducing a top node, which helps version. It's always one node that you will start from, so it's not really expensive. Or you can set it into the properties. Hard challenge. Yeah. We didn't found a proper solution to manage versions of the graph, to be honest. We actually asked business not to put that into a business requirement. Yeah. I'm sorry for this response. Are there any questions? Yes.
Do you have any views on Neo4j versus other providers?
Or like?
Neptune.
Yeah, Neptune, or you have Tiger Graph, or there are more. Yeah. I don't have any views. I've read into them, but I have no production experience on it, so I can't say anything about it. Yeah.
Can a relationship be queried bidirectional?
No, it's never bidirectional. It's always having one direction, but in your query you don't have to specify the direction. So you can actually write down an unidirectional relationship without those thingies, just two dashes. But then you're giving less information to your query planner, so obviously the query will be less performant. Yes?
How do we understand when we need to adopt a new database like Neo4j? We already have Mongo, we already have Postgres,
Yeah.
Redis, and for example, we are building this recipe app.
Yeah.
How do we understand that this model doesn't fit to our existing database and we need to use a graph database?
Yeah, this depends on the questions you're going to ask to your data. Are you really going to query into the relationships? Does it matter? Are you going to do some analytics on it as well? Are you going to do community dissection, for instance, which is really a graph feature? Or are you going to do some path traversal? Those are really graph properties. So then a graph becomes a more of a good solution to go for. MongoDB would be, let me see how again. The most valuable thing is that you can request everything about those relationships and all the paths that you're going to traverse to. One of the clients I've worked with was actually building a navigation tree, a flexible navigation tree, depending on the customer that was going to request. So it was a tree. So then it's obvious that you're going to go for a graph solution. So yeah, it really depends on what you're going to ask to the data.
I'll maybe ask later.
Yeah, that's fine. That's all fine.
Can I ask maybe like a sort of follow-up?
Yeah.
So with relational data, like usually is represented maybe by some kind of front end, say like a portal where you have some fields that are populated by that data,
Mm-hmm.
but the fields are then populated as is. What are some maybe more telling examples of like what kind of front end do you usually have when you have a graph database on the back end? Right?
Yeah.
So you're saying analytics or
Yeah.
thinking of like also like a graph front end or something?
Yeah, there are some graph front-end libraries that you can use to visualize your graph database. I'm now forgetting about which libraries you can use them, but so you had to look them up. But we, at another client, we actually implemented a whole front-end, so investigators could query throughout the graph to discover patterns in the data. So that's entirely possible. You don't need to give them right away access.
They don't go to like Neo4j desktops.
No. No, please don't, because they have no query experience. Yeah. Yeah, no, but I can understand your question because the Neo4j desktop is already really intuitive and feeling like a UI. So your business users, when they discover you're querying on this, they will request access. Yeah, so don't give them that. Give them a front end where you're already pre-filtering the data they're exposed to and let them just click it through. But there are some libraries that you can use to represent the data. Yeah, that probably is used in Neo4j desktop as well. Still a question? Yeah?
About the performance, I wanted to ask. So, because I guess that as many data you have, then the execution time increases, right?
Yeah. Yeah.
Is it like what indices can help with that?
Yeah, indexes can help with that. There are various ways to define indexes, either in your relationships, on your nodes, on the properties they're holding on. You need to define them wisely. The same rules applies as to a relational database. So don't index all your graph, only index the fields that you'll be querying on. Unique constraints will automatically generate an index as well. So those are all the rules that you can follow to tune your queries. Please remember that a Neo4j database also have a caching layer. So some queries will just maybe warm up your cache as well.
Does graph databases allow circular dependency
Yeah.
for graphs? And if yes, is there any way to define restrictions to disallow?
I don't know if you can forbid relationships, to be honest. But maybe you are, but you can create relationships that are pointing to the same identity back. Yes.
So it's possible, but
No.
is it possible to define rules which restrict such?
No, I have to look that up, or you can look that up into the documentation. The documentation of Neo4j is very elaborate. But yeah, you can define circular dependencies for sure. Yeah. If no rules applies. Any other questions, Peter?
Would this integrate better with GraphQL than, for instance, a regular relational database?
No, it's not because, I don't know, no, not for sure. No, it's not because graph is in the name, then no, I'm sorry. I don't know, actually, to be honest, I don't know, but no, it's not an obvious connection to me. Any other questions? Yes. Mm-hmm. Yeah.
With the Neo4j, this problem there is or no?
I've never faced problems with typing. No, in Neo4j, it's been written in Java, I think. It is pretty strongly typed. You can use a lot of types to define your properties and so on. Especially the duration is really nicely mapped from Neo4j to the Java beans. So I haven't encountered any problems with that, no, for sure. Last question, because I'm a bit over time. Yes, sir. Fuzzy matching, yes, there is. You can do fuzzy matching in Neo4j. It has a lot of techniques to do that. Yeah, and you can look that up as well. It's very well. It's using Lucene indexes as well under the hood. So, yeah, that was it. Thank you all for attending. And please rate my talk.